So welcome to our workshop on using the Acacia object storage service. So I guess I guess I'd like to start by saying that we're going to make this workshop fun and interactive. And if you have anything that you'd like to add or any questions, don't hesitate to speak up and to jump in. So I know some webinars can be a bit a bit one-sided or a bit of a monologue, but if we make it a two-way conversation, it can be quite fun. So we're gonna take you through a few lessons, and it's going to start with a presentation on the Acacia object storage service. But then we're going to launch into some tutorials. So that's going to be rubber on the road. We're going to, use what we're learning, and hopefully become more acquainted with how Acacia works. But what I'm going to do first is going to take us through a presentation on using introducing the Acacia object storage service. So I'll just present that, and then I will share my screen. Okay, how is everyone going? Can everyone see that okay?
Yes, Toby.
Yes.
Excellent. All right, so let's introduce the Acacia object storage service. So the focus of this module is to really just define the terms, what object storage is, what a bucket is, what an object actually is, in a way that you'll be able to compare and contrast object storage and file systems. So you may have used file systems, or you have used file systems in the past on your computer, on Pawsey, and these file systems have served us well. But object storage is a slightly different way of doing file storage. So we're going to be able to identify Pawsey's new object storage system and what are the basic principles behind working with objects. So this is a picture of Acacia on the right, and it uses a storage system called Ceph. And so that links, that's the software that provides the glue that runs on a set of rather cheap networked computers. And the beauty of this storage system is it's put together, quite inexpensively, but it can scale, and it can scale well. So object storage is the storage that is in use by cloud providers such as Amazon. And so that's how that they can cheaply get large amounts of storage using commodity hardware. So that's the design philosophy behind Acacia. So lots of fairly inexpensive commodity storage systems that are linked together using software such as Ceph. So let's recap what file systems are. So, a file system is a way of grouping and storing files that is hierarchical. So you'll have folders and you will have subfolders. So here is a folder here, and here is a subfolder, and so forth. And inside that hierarchy, you can store files. So that's what we're used to. That's how we're used to thinking of files. But within a file system, you can open up a file and interactively edit it. So you can open a file, you can append to it, you can change things in it, and then you can save that file. So file systems are built to be able to open files and edit them, and then close those files again. So you can organize files into directories. So they are, folders and subfolders. And the Pawsey supercomputers like Magnus, Zeus, Topaz, and Setonix, they all use shared file systems to store data. So they are file systems that are available from every node in the supercomputer. So a file has associated with it specific metadata, such as the name of the file, the timestamp or when the file was last modified, the location of the file within the file folder hierarchy, and sort of permission attributes, whether or not you can read or write to that file. And you can use this metadata for actions such as finding the largest files in your file system. So yeah, so those are files and the specific set of metadata that is associated with those files. So that metadata you can't actually change. So you can't expand the metadata that can be associated with a file. And that's how object storage is different. So with object storage, you have a standard set of metadata, but you can expand the metadata that you can associate with a file to include your own metadata. So file systems are hierarchical, and the hierarchy can be as deep or as shallow as you want. So here is some folders, and here is a file, and you can see that there can be quite deep hierarchies of files and folders. So how is object storage different to file systems? So first and foremost, object storage is a way of grouping and storing files that is flat. So there's no hierarchy in object storage. You have things called buckets, and they are kind of like folders, but that's where the hierarchy ends. There's no concept of a sub-bucket. So buckets are like folders in that they are an organizational tool. And inside a bucket, you can have a number of objects. So these objects in blue, they go into the blue bucket. These green objects go into the green bucket, and the orange objects go into the orange bucket. But the important thing to know is that, yeah, there's no hierarchy. So how can we then approximate a hierarchy? So what you do is that the name of the objects themselves, so every object has a name associated with it. The object name is flexible enough so that you can prepend a subfolder, even though it's not really a folder. You can prepend the name of a subfolder followed by a / to the name of an object. So even though it's completely flat, you can add as many subfolder names to the name of the object, making the name bigger. And so that's how we can capture the hierarchy of a file system, and that's just by putting the hierarchy into the name. So yeah, so that's how we can do hierarchies, or that's how we can capture hierarchies with a flat storage system. So we've got buckets here, and every storage access on Acacia has up to 1,000 buckets available. And in each bucket, you can have 100,000 objects up to a hard limit of 1 million objects. So there's quite a few objects that you can store in a bucket. Okay, are there any questions on this so far?
No, all good.
All good, excellent. So yeah, so the fundamental concept is completely flat storage, but we can change the name to capture, we can change the name of an object to capture a hierarchy that way. The second thing with object storage is that it does not allow you to interactively change objects. So to change an object, you must fetch it, or what I mean by fetch is you make a copy from storage, and then you modify the file, then you put it back. And when you put it back, you technically create a new object, and that's how object storage works. So there's no concept of being able to interactively edit objects. You can only copy from and push to objects. You can certainly move objects around between buckets, for example, but that is technically creating a new object. So that's another fundamental difference between file systems and object storage. So this concept is called immutability, and that means that an object and a file, so that means the metadata and the data associated with an object cannot be edited in place. So if you want to change something, you have to grab it, do something to it, and then put it back.
I have a question. How about if I just rename the data?
Yep, so you can rename an object, but that kind of technically creates a new object. Yep, go ahead, Alexis.
Yeah, sorry for that. Yeah, it creates a copy when you rename.
Mm-hmm.
Oh,
so
got it.
Yeah, copy and delete the old.
Yes. Yes, that's correct. So when you want to change something like the metadata, what you do is you move it to another object, and that technically creates a new object. And during that move, you have the ability to change things. So yeah, and we'll certainly get into that in the tutorial a bit later on. Okay. Yeah, so the fundamental concept is that we can't do interactive editing of objects. It's a copy from and then push to sort of system. Okay, so let's delve into objects now. So an object has associated with it three things. So this is the data component, the binary data, and it has the name. So that's the name of the object. See how we've got a folder name prepended to the name of the object. So that's a larger name, and that name is globally unique. So yeah, so I guess the third thing that you could say is that everything in your object storage, every object has to have a unique name. And how we achieve that, just going back, is that every bucket name in the system has to be globally unique. So that means nobody else can create a bucket with the same name as a bucket that you have in your storage allocation. So if every bucket is unique and every file within a bucket has a unique name, then that's how you guarantee that every object has a unique key or a unique name. The next thing that you can have associated with an object is metadata. So that might be the size of the object, an MD5 sum, or the time that it was last accessed. So that's a set of metadata, but you can add your own custom metadata to an object. So an object's metadata is stored separately from an object, but within the object storage system. Okay, so this is an object that lives in a bucket, and in this case, the bucket name is AWS in action. So let's now create an analogy between file systems and object storage. So with a filing cabinet, aka a file system, you can locate, copy, edit, and remove files from the filing cabinet. The filing cabinet is really accessible to you and everyone else in the office, but it's difficult to access for someone outside. They would have to get a visitor pass to come and see your office. And then they could access it that way, but it's quite difficult to arrange that access. So a filing cabinet can only hold a limited number of files before you need a new filing cabinet. And to source a new filing cabinet can be quite an expensive process. And it's also hard to keep and search notes about the files themselves. So where do you store, how can you store metadata about your files? Object storage is a bit like a bank vault. So you know how a bank vault works is that anyone from the public, if they have the right authorization from the bank, they can come and access whatever is in the bank vault that is associated with that authorization. So if one of these things inside your bank vault has a certain authorization and you give that authorization to someone else, then they can come and access that particular thing that is inside your bank vault. So it sort of makes storage a lot more accessible to people both outside, with the right authorization, of course, and people within your organization. And so, organizations like Amazon, they use object storage with their S3 object storage service. So, so the vault is shared with all the other bank customers and members of the public. And of course, only people with the right authorization can access the objects. So let's compare and contrast file systems and object storage now. So file systems store data in files with a fixed set of metadata. Object storage stores data and custom metadata in objects, so you can add in your own metadata. A file system allows you to make changes to a file in place. So you can open a file, you can do things with that file and then save that file. You can make an in-place change. Object storage does not allow you to make in-place changes to objects. You have to fetch a copy of the object, make a change, and then put the object back. And as I said before, you can change the metadata on an object. And there is a flat file storage or object storage system in object storage. Object storage is best suited for retaining massive amounts of unstructured data. So with object storage, there isn't a a largest or a smallest file, or sorry, object size that works well. You can store everything inside a object storage system. So you can store large files, you can store small files. There's no big issue with doing that. With file systems, if you have lots and lots of really small files, you can degrade the file system storage performance. So yeah, so uploading lots and lots of small files to an object storage system is okay. It's just that every time you upload something to an object storage system, you actually create a new HTTPS connection, so an encrypted HTTP uploads and downloads. So that's how you get files in and out of the Acacia object storage system. So with that said, object storage isn't really suited to frequently changing transactional data. Yeah, just because with that you need to be able to open a file, edit it in place, and then quickly put it back. A file system has upper limits on expansion, so it's not really scalable. So if Pawsey, got to their storage capacity with Acacia, they could easily add more hardware and increase the capacity of the storage system. But that's not so easy to do. It can be done, but it's not so easy to do with a file system. So let's introduce Acacia now. So Acacia is meant to be the central object storage service for Pawsey projects. And it can be likened to the concept of cold storage, warm storage, and then hot storage. So what I mean by hot storage is that hot storage is a really fast file system where you can rapidly make changes to things. And that is designed to be the scratch file system, for example, on Setonix. So that is a hot storage system. Acacia is meant to be a warm storage system. So that means that it's still fairly quick, and we're talking hundreds of megabytes a second instead of, maybe a gigabyte or two a second. But it's not as slow as tape storage. So Banksia is meant to be tape storage, and that's meant to store things longer term. So that would be called cold storage. So Acacia is meant to be warm storage. So that means you can access it fairly quickly, and you can, what I mean by fairly quickly is with fairly low latency. And you can also upload and download things to it fairly quickly as well. Acacia is meant to be accessed not only by Setonix, Nimbus, Banksia, and the visualization, but also accessible from outside. So if you're in the office and you have a laptop, you can access Acacia directly without having to log into Setonix first, for example. So yeah, so that's the reason why Acacia is what it is. It's providing a warm tier storage service for Pawsey. So we may have covered some limits before, but Acacia allows for up to 1,000 buckets per storage access. And there's two kinds of storage access. There is user storage, which is 100 gigabytes. So every user with access to Acacia has their own allocation just for them of 100 gigabytes. Every project that is given access to Acacia has a terabyte of Acacia storage per project, but you can always ask for more storage if you need it. Acacia uses access keys. So they're like a username and password. So it uses an access key, and every access key is associated with a storage. So with a storage allocation, such as user storage or project storage. So there's two kinds of storage. There's user storage and project storage. And the access key determines which lock is used. So users interact with Acacia using the Amazon S3 protocol. And so that means that tools that have been developed for use with AWS S3 can also work with Acacia. And these tools that we're going to teach today are the MinIO client and the Rclone client. I think we also covered this, but every bucket can have up to around 100,000 objects, and there is a hard limit at 1 million objects. So I think we'd sort of prefer that there be less than 100,000 objects per bucket. On the left here is the storage sizes for Acacia and Banksia. So we've got 60 petabytes available of object storage currently for Acacia, but you can cheaply expand that if we need to. So Banksia is the cold storage, and that uses tape. All right. So now we're going to walk through a series of tutorials on how to use Acacia, both from the command line and as part of your HPC workflows. So the first tutorial is going to be just about getting access to Acacia. So setting up clients to access Acacia from your computer and Pawsey systems. The next one is, okay, rubber hits the road. Let's use Acacia from either your computer or Pawsey. So we're going to be working with buckets and objects. So we're going to be copying things up to Acacia and back. And we're going to show you how you can share your data with colleagues using publicly accessible links. The last tutorial is about using Acacia in your HPC workflows. So we're going to be talking about tar files and how to use them, but also how to set up dependency flows so that you can bring things in from Acacia to Setonix, do work using your supercomputer job, but then push the results back out to Acacia. So I've just finished the tutorial now, but were there any questions surrounding that? All right. So what I might do now is just take you through getting access to Acacia. So can everyone still see my screen okay?
Yep.
Yeah, I'm going to close that down now. So if we unpack the Acacia training.zip, so if you've already got the course material unpacked, yep, there should be a set of folders here. And we're going to go to T1, getting access. And if you click on L1 access keys, okay, so we're just going to talk about how we can get those access keys to Acacia. So has everyone got this course material loaded?
Yep.
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 Excellent. All right. So yeah, as we were saying, we use access keys to access a particular storage allocation. whether it be your user allocation or your project allocation. Each connection to Acacia requires these two pieces of information that make up a key pair. So the access ID and then your secret key. So those two bits of information form your key pair that you can use to access a storage allocation on Acacia. So you can have up to 5 of your own key pairs active for any storage allocation at any one time. And there is no need to share your keys amongst your group, because every one of you in the group will have the ability to make your own keys to get access to either the project storage or your own personal storage. So a Pawsey account with a working password is of course essential, but how we get our keys is we go across to this site here. So that's portal.pawsey.org.au. And I'm going to go there, and if you feel like, you can also go in your web browser to portal.pawsey.org.au. Now, some of you might have Acacia access keys already, or sorry, some of you might have your access to Acacia already set up for you. So I'm just going to log into my own. Okay, so that is my own, this is my own area. And what I'm going to do now is I'm going to click on this Acacia tab. So we're at portal.pawsey.org.au. And the Pawsey folk refer to this as origin, this site. And this is where you can get your access keys for Acacia. So I click on the Acacia tab, and in this little section here, I've got all the different projects that I have access to. So you'll see something similar. You'll see your username, but I have access to the Courses 01 project and the Pawsey 0007 project. So I'm going to click on the Courses 01 project. And I can see here that in the Courses 01 project, we have a terabyte of quota, and at the moment there is 3 buckets and 1 object in there. So this is how you can see what buckets you have and how many objects are in those buckets. So what happens if I want to make a key? So you can go here to view keys, and I can choose my storage. So I'll go to Courses 01, and you can see I've got 2 keys here already. And that's the access ID, but you can't see the password or the secret key. So if I want to make a new key, I go create new key, and then I click yes. And there we go. So there's my access ID, and there's the secret key. This is the only time that a key or the secret key would be visible, is when you create the key. So what you can do is you can save this information to a file on your computer, and it's best practice to never ever put a secret key hard-coded into your code. So you can put this into a file by itself, and you can source that file from your scripts. So yeah, so we never put our secret key or access never put our secret key hard-coded into our scripts. In the drop-down menus here is just some quick links, or sorry, some quick ways of configuring the MinIO and Rclone clients for use with your access ID and secret key. So you can copy paste this information to your account. So if you're logged into Zeus or logged into Setonix, you can copy paste this information into the command line, and then that will set up Rclone and MinIO client to use this access ID and secret key. So that's a bit of a shortcut. So that's quite useful. So when you create the key, that's the only time that the key is going to be visible. So I'm going to close that now. And I think this key here is the key that I just made. And so I am free to delete that key if I want to. All right, so that's how you are going to get your key using your for real credentials. But today we're using training accounts. And so your training account doesn't have access to Origin. So that's why your keys have been emailed to you separately in preparation for this workshop. But if you're using your for real account on Pawsey, you would get your Acacia access keys by going to portal.pawsey.org.au. All right, are there any questions surrounding this one? All good?
All good.
Great. Yeah, it's a fairly straightforward process to get your access keys for Acacia. So once you have your key pairs, and just to reiterate, you would have been emailed your key pairs for today's workshop. Once you have your key pairs, there are some best practices. So never embed your access ID or secret key in programs or scripts. And that's because people like to search GitHub for these access IDs and secret keys and exploit them. So that would be a security hole. You'd never leave the keys to your house lying around in a shopping center. So we never put our access ID or secret key into programs or scripts that might make their way to the general public. Always store your keys in a file that is readable only by you. So on Pawsey, you can make sure that it's readable only by you by using the chmod 600 and then the name of your file. So that's the file that contains your access ID and secret key. You can also use environment variables to store your access ID and secret key, and you can bring those environment variables in through a script, and that's fine. That's good practice. It's also good practice to change your access keys periodically. I'm certainly going to remove that key that I created after the end of this workshop. Delete keys you no longer need, and you don't need to share your keys with anyone else. So yeah, so that's good. The next step now is to get access to the Pawsey system. So in this case, we're using Zeus today because Setonix is offline while they upgrade it with a new set of GPUs. So it's going to be really exciting when that's complete. But today we're using Zeus, zeus.pawsey.org.au. And those of us who are attending, I know that you already have access to Zeus. or that you've tested access to Zeus using the account credentials that were emailed to you. So yeah, I don't think I need to cover this because you already have access, but for people on the recording, inside the L2 SSH access page, you can get instructions for logging into Pawsey computers using an SSH client that is available to your operating system, whether that be Linux, Mac OS, or Windows. So there are some instructions in the T1 getting access folder, L2 SSH access. All right. So any questions surrounding this one?
All good.
All good? Yeah, that's fairly straightforward. So let's now set up the MinIO and Rclone clients using the login that you got. So I'll get everyone to log in to Zeus if you're not already logged in. And I'm going to do the same. So I'll bring this to a new view. All right. So I'm just logging in now. Yep, so I'm logged in as the trainer account. And let me know when you're at the same place. So let me know when you're logged in as well, and you can see a command line prompt.
Yep.
Yep.
Excellent. Okay. So the first thing that we need to do is load the modules for the MinIO client program. So that is MC, but we need to see which module is available. So on Zeus, you used to be able to, or on Zeus currently, and Magnus, you used to be able to just go module load MinIO CLI. And that would load the default version of the MinIO command line client. But Setonix doesn't have a default module. You have to choose explicitly the version of the module that you'd like to load. So let's go module spider MinIO CLI, and that tells you what versions of the MinIO client are available. So in that case, it's this one. And so we go module load MinIO CLI with that version. And I now have access to the MC command. So that's the MinIO command line tool. We call that tool MC, or it's known by the name MC. And we can get help for any of the commands that MC has by going MC, for example. ls is a command that the MinIO client has, and we just want help on that command. So we can do that and get some help on any command that MC uses. So that's how we can get help. So it's either MC help or MC followed by the command that you'd like some help on, and then the help flag. So for today's module, you can add, or for today's tutorial, you can add this module load command to your bash RC. So I'm just going to copy that. And then we're going to use the nano command, followed by a tilde, followed by a /, and then .-rc. So whenever we log into Zeus, this bash rc file is read, and that's used to configure your shell. Oops. Okay, so nano is not available. Well, that's interesting. We have to module load nano. Okay. So I'm just having a look at my bash rc, and can you see how I've put the module load MinIO CLI command in there? So what I'll get you to do is to also put the module load MinIO CLI command into your .bash rc. And yeah, let me know if we have any problems with that. You'll need to do a Control-O to write out the file, and then a Control-X to exit. So we need to module load nano, and then we need to go nano space tilde / .bash rc. And you can just put the module load command at the end of your .bash rc file. While you're there, we also need to load the Rclone client. So yeah, while we're here, let's just module load the Rclone client as well, because we have to go through the same procedure to get the version number for the Rclone client. And I already know that it's 1.58.1. So you can just put that line in as well. Module load Rclone 1.58.1. All right. How did we go with that?
Once we've written it and we
Yep.
write it out,
Mhm.
so it's Control-O, and then what's
Yep.
the next step?
Oh, yeah, so we go Control-O to write it out.
Yeah.
You go Control-O to write it out, and then Control-X to exit. Yep.
I feel like I'm doing something wrong because I do Control-O and then Oh wait, no, I got it.
Oh, that's all right. Yeah.
So just one comment about this, Toby.
Mhm.
And guys, I guess it's fine for the training to do this, but we at Pawsey rather not suggest to load modules and set up environment in your Bash RC.
Yes.
Just because when there is an issue and users submit a ticket, then when we try to troubleshoot, we do it on our own accounts. And obviously, then the steps that the user, the environment and the setup the user is following is going to differ from ours.
Yeah.
I guess this this sort of a recommendation or a best practice come a long time ago when people were trying to troubleshoot problems, and at the end, I don't know how many times the issue was coming from a setup in the Bash RC from the user. So we rather any module loading or any other environment setup to be in the Slurm Bash script or in the scripts.
Yep.
Rather than in the Bash RC. That's the thing. So it's fine. It's fine for today, but I guess it's better to avoid this kind of practice for real use of the supercomputers.
That's correct. Yes, indeed. You know, during the time I was using this, I certainly ran into, you know, problems with putting things into my Bash RC and trying to have folks troubleshoot it. Yeah, because your environment can get very specific. So yeah, that's definitely good practice, is to always put your module load commands into the supercomputer scripts, you know, your job scripts that you're using. Yeah, so I think the only reason why we're doing this for today is just for convenience. So yeah, it's definitely good advice not to put module load commands in your Bash RC generally, but just for today, just so that we can have quick access to these commands, we're just going to put those module load commands in. Yeah. All right. So has everyone been able to get those module load commands into your .bash RC?
Yeah.
Excellent. So then what we can do is we can log out by pressing Control D and then log back in using your account credentials. And you should have access to the MC and Rclone clients without having to do the module load yourself. All right. So was everyone able to successfully log back in?
Yeah, got it.
Got it? Cool. Okay. So the next step, once we've been able to log back in, the next step is to configure the MinIO client for use with the access key and the secret key that was emailed to you this morning. So see these set of commands here? So the configuration for MinIO client is stored in a directory called .mc, and that's in your home folder. So what we're going to do is we're going to make that directory first. So we do mkdir, so we can just copy paste this command. So we make that directory .mc in our home folder. And then we do this command. So we turn off history capture. And that is so that when you copy in your access ID and secret key into this configuration, it won't be visible in your history. So that's just a security measure. So the next step is to copy paste this command here. Oops. But what we're going to do is replace $access ID. So we're going to replace that access ID and that $secret key with the access ID and secret key that was emailed to you. So this is the MC alias set Acacia mine. So what we're doing here is we're telling MC to create a new access to Acacia, and we're going to give it the name Acacia mine. So Acacia-mine. And the endpoint is projects.pawsey.org.au. And then we're going to use the access ID. So we copy paste the access ID into there, and then we copy paste the secret key into there. And yeah, how did we go? How did we go with that?
Yep, I'm done.
All good? Excellent. So if that worked, what you can do is go MC ls Acacia-mine. And if it doesn't report a problem, then that is okay. Then your configuration is working. Now, there is a bit of a problem with MC in that if you don't get the alias name correct, what it actually does is treat your file system as a valid destination for doing things. So yeah, it's very important that we're going to get the alias name correct. All right, so was everyone able to run that command okay?
Yep.
Yep.
I have an error, is no such host.
Oh, okay. So do we get the thing right? https://projects.pawsey.org.au.
Oh, I think I typed. Give me a second.
No worries.
Oh, got it.
Got it. Hey, good on you. That's excellent. Okay, so it looks like both of you have MC configured now. And what we can do is we can go and have a look at the configuration file. So if I go to .mc, change directory to .mc, okay, then I go ls. See how there's this file called config.json? So if I nano that configuration file, config.json, oops, module load nano, So if I have a look at that configuration file, that's what it looks like. So that's what the configuration file for MC looks like. So you've got your aliases here. So each alias is a captured key pair, and you can use that alias to access a resource. So in this case, we've called our alias Acacia mine, and there's the secret information associated with that particular alias. Okay, was everyone able to see the config.json?
Yep.
No.
Oh, okay.
It says if nano is not a typo, you can use this command
Oh,
at the
yes.
bottom to look up.
Oh, yeah, we'll just have to module load nano.
Again,
Yep.
yeah.
Yeah, that's right. We won't be using nano too much, but yeah, you'll just have to module load nano every time you want to use it. I mean, you can use your own editor. You use your own editor that you like using.
Okay, yeah, now I can see it.
All good? Yeah, that's cool. Okay, so we just tested our connection to Acacia. So awesome, well done. So that's how we can set up our access to an Acacia storage allocation, whether it be our user allocation or our project allocation, is to use this MC alias set command, and that sets up our thing. So there's one more thing that I find really useful to have is auto completion enabled for MC. So if you type in this command here, or just copy paste that, MC -- auto completion, what that does is that edits your .bash rc. That edits your .bash rc to have this complete command. Can you see this complete command? So that should, when you run this command here, that should add this line to your MinIO client. Oh, sorry, that should add this line to your .bash rc. So try running that command and then look at your bash rc again and see if you see this line here. How did we go with that one?
Yep, got it.
Got it?
I think I got it.
Yeah. Yeah, so once we've done that, we can restart our shell again or log in again. And then once we've done that, we should be able to do MC ls and then start typing Acacia and then press tab, and it will complete the rest of the line for us. So I find tab completion to be really useful, particularly when I'm looking through directories from the command line. But you can also use tab completion with with MC as well. Okay. Now let's work with the Rclone client. So we got the MinIO client configured successfully. The next step is to get the Rclone client configured.
I'm back.
Now the steps. Oh yeah, go ahead. Sorry. Yeah.
I was just saying I was back.
Oh, yeah, no worries. Yeah, so the next steps now are to get the Rclone client configured. And we already put our module load for Rclone into the .bashrc file. But what we need to do now is configure the Rclone config file. So we're going through the configuration instructions in sort of the hard way, but these configuration instructions will work across any system. So that's a Windows machine, a Linux machine, or a Mac OS machine. So you can use these instructions, these configuration instructions, on any machine. I think remember that we talked about when we were making the keys in the Pawsey user portal. So I'll just log in again. Yep. So if we just log in again and we try and make a new key. So let's try and make a new key here. These instructions here will create a configuration file for you for both Rclone and MinIO client. So yeah, those are the shortcut ways to do configuration, but only on Pawsey though. Or Pawsey and Linux systems, yeah, and Mac OS, but maybe not so much with Windows. So we should have access to Rclone now. Rclone -- help. And we can do an Rclone ls -- help. And that's just the help for the ls command within Rclone. Okay, so there are some instructions for installing Rclone on Windows and Mac OS. So we can certainly follow those when we have a spare moment, and you can configure Rclone on your computer with your for real Acacia credentials if you have them. But while we're logged into Zeus, we're going to configure Rclone with the credentials that were emailed to us. So let's go Rclone config. And that brings up this little tool to create different configurations. So Rclone Rclone calls an access a remote, but MC calls an access an alias. So an alias or a remote are one and the same thing. So in order to make a new remote, so we're going to go N. So we type N for new remote and then enter. And then we give it the name Acacia Mine. And my remote already exists, but it should be okay for you. And so the next thing that you need to enter in after the name, so you type in Acacia Mine and then enter, and then it should give you a prompt for storage. We're just going to enter in S3 and enter, and then it should ask you for the provider. we use Ceph, and then this env auth, we just provide the word false. And when it asks you for your access key ID, you're going to put in the access key ID that was emailed out, and the secret access key that was also emailed out. So yeah, that's the information that we enter in. Now, if anything is blank inside in this little table here, that means that we don't enter anything into the question. And for the endpoint, we have https://projects.pawsey.org.au. And then finally, it should get to, would you like to edit the advanced config? You just say N for no, and then you press enter to accept the new remote, and then Q to quit.
Is there a way to go back a step?
When you create a remote, you can always delete it. So yeah, so I'm just going to delete the existing remote that I have, the Acacia Mine remote. Yeah, let's do that. So I'll delete. Oops. I'll go back. I'll start Rclone config again.
So I should just delete and start again?
Yeah, you can delete the remote and start again. So I'm just going to copy the remote. I'm going to copy my remote to a new one and then rename it. So I can make a new one. So I'm going to copy Acacia Mine. Okay, cool. So I can now delete my Acacia Mine. So I'm going to delete Acacia Mine. So now I don't have Acacia Mine. So here I go, new remote, and give it a name, Acacia Mine. And when it's asking me for storage, I go S3. When it's asking for a provider, I just enter in Ceph. When it's asking me for env auth, I just type in false. And now when it's asking me for the access ID, I just type in the one that I was given. And the secret key, that's also the one that was given. Okay. Do we use the region? So there's nothing there for the region. So we just type enter. And then when it says endpoint, I'll just copy paste projects https://projects.pawsey.org.au. Yep. Nothing for the location constraint. Nothing for the ACL and server-side encryption. And then we go nothing for the SSE KMS key ID, and we don't want to edit the advanced config. And then we say yes, this is okay. And if you made a mistake at any of those steps, you can always edit a remote. So I'll just say yes, that this is okay, but I can go E for edit existing remote. So I can go E, and then it will just ask me the questions again. So in this case, the provider was Ceph. False. And I've already put my access key ID in before, so I just press enter for what it was before. Same is true with the secret key. And nothing for the region. And then our endpoint is https. Yep, so projects.pawsey.org.au. And then we leave the location constraint and the ACL. Server-side encryption. No. Yes, this is okay. All right. So when we've been through the process of configuration, we should have this remote here configured. Is that what you see?
Yeah.
Excellent. Okay, then I can just go Q for quit. And we should be back to our command line. And then testing the access is you go Rclone ls Acacia mine, and then followed by a colon. And if that doesn't produce any errors, then we're all good to go with Rclone.
Got that.
Got it? Excellent. And we'll do one final thing before I'm just gonna, I think we should have a little break for morning tea after this, but we'll do one more thing before breaking for morning tea, and that is to enable auto completion for Rclone. So all we have to do is copy paste this command in. So we go rclone gen autocomplete bash. So we're making an autocomplete script for the bash shell, and we're storing it in our home bin rclone autocomplete file. So we do that. And then the next step is to edit it, or edit our .bashrc. And we can copy this line here into our .bashrc file. And that will allow us to do command line auto completion for Rclone as well. And that's because, command line auto completion is pretty helpful. How is everyone else tracking? We got Rclone configured correctly and got the autocomplete going.
Yeah.
Yeah. Oh, great. Oh, that's awesome.
Same here. Got it.
Got it. Brilliant. You guys are awesome. Yeah, that's really cool. So the next step is to, well, let's download the course material onto your Scratch space in Zeus. So what we do is we change directory to Scratch, courses 01, user, and we're going to use curl to copy the training material to that folder in Scratch. And the reason why we're doing this is because we need a copy of the training material on Scratch so that we can upload and download the mock data. So I'm just going to go, I already have the zip file, but I'm just going to remove it. And then we're going to go curl. And so we'll just copy that command, but where it says training URL, we have to copy the link that is in the welcome letter or the Zoom chat. So it should be the same link. But if we copy that to copy that straight in. So I will just, okay, we've got a huge link in there, but that link must be enclosed in these quotes. So in these double quotes. See how we've got a double quote there and a double quote there? So if you just go curl and then double quote and then that massive link and then followed by an end double quote. And then you have the command line argument output, acacia training.zip. So that should download the course material to your Scratch directory. The next step, once that's downloaded, is to go unzip acacia training.zip. And that will unzip the
Can you go
files that.
back?
Yeah, sure.
So it's curl.
Mhm.
And then what's
Yeah.
the training URL?
Oh, okay. So the training URL, that's either in the welcome letter, so you can copy that link, or I've just put it in the Zoom chat.
Oh, okay.
Yeah. So I'll just copy that. I'll copy that link to the Zoom chat again, just by itself. There you go. Yep. Yeah. So you go curl, and then your double quotes, and then that massive link there, followed by end quotes, and then output acacia training.zip, and then that should download the zip file, and then you unzip it by going unzip acacia training.zip. And then we can change directory to Acacia Training data. And we should have the simulation directory all there. So if we go to the data directory, see how so we go cd data, and there should be the simulation directory already done. But if the simulation directory wasn't there, you could have unzipped the data.zip. So we're all set. So we just go to results, and then we should see the data 00.dat and so forth. Do you guys see those files?
Yep.
Okay, cool. The log directory, there should be some log files there too. So this directory, so we'll go back to the data directory. This directory simulation is just some mock data. So there's some binary data there, and there's some text file data. And that's what we're going to use to upload and download things from Acacia. So we've done that step, and you can always find the instructions for copying this data in the L5 mock data tutorial. So that finishes our first tutorial, which is getting access to Acacia and getting the data prepared. The next tutorial, so we go to Acacia training, T2 Acacia from the command line. So this is just on your computer. And let's open the simple usage notebook, or the simple usage HTML document. All right. So the MinIO client is the preferred supported client for Acacia. And I use that word very loosely because I think folks are able to use anything that speaks S3, but Pawsey is officially supporting the MinIO client and to a lesser degree the Rclone client. So the MinIO client is the preferred supported client for Acacia, but the Rclone client has some advantages. In fact, either client has some advantages in particular areas. The MinIO client is better at working with metadata, but the Rclone client is sometimes better or more stable for large transfers that need to be done quickly. So it's better to become comfortable with both clients and use the strengths of each. There's no one client that is going to provide ease of use, power, and in some instances stability all in one client. So you kind of have to use a mixture of clients to get what you need. If you'd like to be a power user of Acacia, you can always look at the AWS command line interface or the AWS Bolto 3 Python library. So if you want to be a real power user of Acacia, you can use those libraries. So we're just going to walk through a tutorial now on how to work with Acacia using the MinIO and Rclone clients. So we're going to explore working with buckets. So we're going to create, list, and remove buckets. We're going to work with files and metadata. We're going to copy simple files, multiple files. We're going to add and extract metadata. And we're going to construct URLs for downloading and uploading data. So sometimes you want to share the data that you have on Acacia, and it's just a simple matter of creating a link. So you know that link that we had a little bit of problems with before, that was actually a link to the course material which is hosted on Acacia right now. So you can construct URLs to things that are on Acacia, and you can send those URLs to colleagues. So that's one way that you can make things available without having to give someone access. So that's that's a way to give access to a single thing within Acacia. And there's other things you can do, such as removing objects and synchronizing directories. And we already covered getting help for the MinIO client. So that's just MC space -- help. But we can do the same with Rclone as well. And you can get help for each of the commands that are available. So go Rclone, and then the command that you want, then -- help. So as an exercise, I'll get you to look up the help for the MB command with MC, and look up the help for the mkdir command with Rclone. So I'm going to follow along as well. So that's the command for getting help for MB. And what MB does is it creates a bucket on Acacia. So MB stands for make bucket. If we do the same for Rclone, so we go Rclone mkdir, so make directory, help. Rclone is meant to be a successor to rsync. So I don't know if you've used rsync before. So it's quite general in the online storage systems that it supports. MinIO client is more specific to, for example, Amazon S3 storage systems. So its syntax and its subcommands have that flavor about it. So once we've looked up the commands for help, let's actually go ahead and make a bucket. So buckets are basic containers for grouping objects. So we've discussed that there's no concept of a sub-bucket. So the similarity to a folder ends there. A user or project can have up to 1,000 buckets, and up to 1 million objects may be in a bucket, but less than 100,000 is preferred. So here's some clues or some good practice for how to create buckets. So a bucket name must be unique across the system. So if I create a bucket, then no one else can create that bucket with the same name. Bucket names can potentially be made public using these URLs. So a bucket name must not contain any confidential information. So your Pawsey username, that's confidential information. So including a Pawsey username in the bucket is not a good idea, but you can include your initials, for example, if it's not part of a username. So usernames can be a target for an attack, so that's why we never put our usernames into a bucket. Email addresses can, of course, be exploited. Never put your passwords or secret keys into a bucket name. So that's not good practice. And initials are okay if they aren't a Pawsey username. Bucket names have to be between 3 and 63 characters long. They must begin and end with a lowercase letter or a digit. Bucket names have to be lowercase, but they can contain letters, numbers, hyphens, and periods or full stops. in order to not have a problem with uniqueness, it's also good practice not to format a bucket as an IP address. So that would eventually cause a problem for uniqueness. But here's a good bucket name. So your project name, that's perfectly acceptable to include in a bucket name. So courses 01-Acacia-workshop 2022. So that's a valid bucket name. So if I've got, I'm going to create a bucket, and I'm going to call mine export bucket name is equal to courses 01 Acacia TMP. So that's my initials. And that's going to be my bucket name. And if I don't already have this bucket, I can just copy paste this command in to create my bucket name. So there we go. So it's made a bucket called courses 01 Acacia-TMP. So that's the bucket name that I've chosen. But what I want you to do is to make your own bucket. And you can save your bucket name as an environment variable by going export bucket name equals to the name of your bucket. So yeah, so try experimenting with making a bucket. You can even make a few buckets if you like. But try making a bucket that already exists. So why don't you try making a bucket called courses 01 Acacia TMP and see if that works for you? When we run the bucket making command, we always specify with MC the alias name. So in that case, we've chosen the alias name to be Acacia-mine. And you have to get that alias name correct. Otherwise, it will use your local file system as a valid storage location. So it will actually make a directory called Acacia-mine in your file system. So if I go ls and I try to mess up the name of the alias. So if I go, instead of Acacia-mine, I'll go Acacia-mines. And it says that it has made the bucket successfully. But if I go ls, I can see that there's actually a directory called Acacia-mines in my local file system. So if you get the alias name wrong, you can inadvertently mess around with files on your file system. So I'm going to remove that directory.
I have a question. So
Go ahead,
after
Michael.
I created the buckets, right? Is there any quick way I can do a quick check whether if the bucket has been created successfully or?
Yeah. Well, what you can do is you can go MC ls Acacia-mine and see how it's got that bucket there. So it's listed my bucket. But I can also just do a quick check of my local file system just to make sure that that bucket name, that I haven't got the alias wrong.
Okay, got it.
Yeah. You can check with Rclone as well. So if I go Rclone ls Acacia mine, but with Rclone, I have to put a colon there instead of a /. Rclone ls by itself only lists objects, but you can go lsd to list directories. And there's the bucket there that we've made. So how did we go? Did everyone successfully make a bucket?
Yep.
Ah, brilliant. Yeah, sometimes the most difficult thing is coming up with something unique for a bucket name. Okay, did anyone try and make the bucket courses 01 Acacia TMP?
Yeah. And it just
And
said
did
that
it
the bucket already exists.
correct? Yeah, yeah, so you won't be able to make a bucket that someone else has. So it enforces that uniqueness for you. Okay, so once you've got a bucket name, we're going to use this export command so that the bucket name ends up an environment variable. So for me, the command will be export bucket name is equal to courses 01 Acacia TMP, but your bucket name will be different after the equal sign. But once you make that bucket name into a environment variable, then you can just copy paste commands in the course material. So what I'm going to do now is this part of the course is going to be largely self-directed now, because doing things together is great, but it can be a bit slow if you're, naturally quite quick at things and you want to explore. So once we've got our bucket name, what we can do is just explore the rest of this tutorial at your own pace. And you can copy commands and paste commands from the course material. And then you can try things, you can try breaking things. You can see things that are useful to you. And I'm going to be on hand in case anything goes wrong. And then I will just quickly walk through the course material with you at the end. But if anyone is having a problem, don't hesitate to speak up. I'm on the audio, so I'll be able to hear. I'll be able to hear if there's any problems. So go ahead. Yeah, so go ahead now and just do the rest of this tutorial at your own pace. Oh, well, welcome back, everyone. I trust the lunch break has been good and we're ready to power on through the rest of the tutorials. All right, so let's get on to the recap. Yeah, so how did you find how did you find it? How did you find the tutorial? Was there anything that stood out to you or anything that was kind of interesting?
For me, it's about the same. I would say like about the similar or same to what we use the command in Linux. You just have to add on like MC in front.
Right. Yeah, MC is quite quite set up like that, but Rclone as well. So yeah, I think you've got the Rclone mkdir, for example, for making a bucket. Yeah. So what I might do is, yeah, let's just have a recap. Okay, so we've got at the start, we've got some instructions on how to make buckets, and I think we already covered that. Bucket names must be unique. And then when we started off the tutorial in the self-paced section, so there was different ways of listing objects. So ls just lists objects only with Rclone, but LSD lists both buckets and pseudo folders. And the one thing I've noticed with Rclone is that it kind of treats pseudo folders as folders. So any object with a name that includes that same folder is treated as being in a pseudo folder by Rclone. So for example, I could go Rclone ls Acacia mine, and then a bucket name, my bucket name, and then test, for example, and that would list every object that has, so every object inside bucket that has the text test / in front of the object name. So Rclone, and I think MC as well, they also treat pseudo folders as like folders. So they group objects into pseudo folders. You can also use Rclone and MC to list objects and buckets in JSON format. Well, I think at least with Rclone anyway, you can do Rclone ls JSON, and then that will list your contents of a pseudo folder example or the contents of a bucket in JSON format, which you can then pass using other tools. So removing buckets, there is, if your bucket is full with something, you can use the MC RB remove bucket with the force option, and then that will remove any bucket that has things in it. But you can also use Rclone purge as well. So we know that command is dangerous. So both programs support the dry run option. So you can do a dry run to test what you're going to remove first. So we unpacked the mock data, and there was just some information here about the limits of objects. So there's no minimum or maximum limit on the size of objects, but just the number of objects. And objects may contain, so /. So that's how we do pseudo folders, is we have the name of the pseudo folder followed by a /, and that's prepended to the file name. We can have exclamation marks, hyphens or dashes. We can have periods, asterisks, single quotes, and even open and close parentheses in our object names. So it's quite flexible in what we can put into Acacia, into the Acacia object names. Then we moved on to simple copies to the object store. So, as you were saying, it's often very similar to Linux commands. So the mccp or copy our data to our alias, followed by a / and then followed by the bucket name. We can also do a similar thing with Rclone, but with Rclone, we have to remember that it's got a colon instead of a / after the alias name. So that is a way to copy simple files or single files to Acacia. And when you're using the cp command with MC, it always copies the file again. But when you are using copy with Rclone, it works more like rsync and only does the copy if the size or modification time have changed. So that's just for the copy command. And you can copy from Acacia by having the Acacia source or the Acacia destination first, and then we're just copying this file data00.dat to your local file system. So that dot means just this directory. But there is a thing here when you're using Scratch. So when you're copying files from Acacia, so that's from Acacia to Scratch, MC does not by default retrieve the modification time of files, but Rclone does. And this can be a problem because it can be a problem for Rclone. Because if you've got something that lives on Acacia and it is older than 30 days, if you try and copy that file without any options from Acacia directly to Scratch, it will be deleted either immediately or almost immediately because the modification time will be older than 30 days. So Rclone tries to bring across the modification time of your files from Acacia. So this can be a problem. So when copying files from Acacia to Scratch with Rclone, you can set this flag local no set mod time. So see how we're copying a file from Acacia to the current directory, but we are setting this flag local no set mod time. And then that will stop the old modification time from Acacia being copied across to Scratch. And that should stop it from being deleted straight away. So there's a big gotcha that Ash sort of raised from the Pawsey team. So we talked about pseudo folders. So pseudo folders are really just the folder names prepended to the name of the object, and then that becomes the new name of the object. So we're copying a file here into a pseudo folder called test inside our bucket. And in reality, all we're doing is just prepending the word test / to the name of our object. But that gives Rclone and MC a way to work with pseudo folders. So every file object that starts with test / you can list all the things inside that pseudo folder. So that was this example here, is copying a file into a pseudo folder on Acacia. Both MC and Rclone can use checksums to copy data. So that's really useful if you want to be absolutely sure that you have done the copy correctly. So maybe if you're over a dodgy link or something, you can use MD5 checksums. So with MC, the flag is --MD5, and then that will copy the data from data00.dat to our bucket, but use MD5 checksums to make sure that what's on Acacia is what's on the local file system. With Rclone, the flags usually go at the end of the command, but what you do with Rclone is you have the --checksum argument, and then that uses the MD5 checksums. Copying multiple files using MC on Linux, so a Pawsey computer, you can use wildcards. So it works just like the Linux file commands, or yeah, the commands to work with files on Linux. So you can do regular expressions to grab all the data files that start with 0 and then one character. So 0001 up to 09. So those files will all be copied to our bucket. But on the return journey, there doesn't appear to be an equivalent way of selecting multiple files using regular expressions. So this is where Rclone's kind of handy. You can't send multiple file names to Rclone, so you can't do this. But you can use this include flag. And then that will select files using some common regular expressions. So in order to copy the data 00 to data 09.dat, so all those files inclusive, we use the include flag, and then we can use this regular expression sort of syntax here. So it's more like wildcards instead of fully instead of fully functional regular expressions. So you can use some basic regular expression syntax. So that will include those files. And when I'm copying from Acacia, we can also do the same thing. So in Acacia, we're copying everything inside bucket name that starts with data 0. .dat. So we're copying all those files from Acacia to the local file system. You can, of course, move objects. So this is maybe where it tripped up Josephine, was that we had originally created. I mean, it's possible. I'm not entirely sure, but with this command here, we would have moved a file to the temp file in Acacia, and then we're using Rclone to move that back. But if that temp file is still on there, then when we try to move again, it may not have worked. So yeah, when you're moving files, I think you need to make sure that the destination file is not there. So when working with metadata, Acacia has the ability to associate metadata with objects in the form of key value pairs. So this is very useful because the right metadata might save an expensive retrieval operation. So we had rot nest and winter, that was our metadata, and we can include that metadata when we copy the file. So metadata, like the data associated with an object, is immutable. And that means that you can only change the metadata when you create a new object. So moving is technically creating a new object. So this is how to incorporate the metadata using MC, and this is how to incorporate the metadata using Rclone. So with Rclone, your metadata comes in on HTTPS headers, or HTTP, sorry, headers, and the header starts with X, AMZ, meta, and then your key, followed by a colon, and then your value. And so you can have as many of these as you want to, but I think the limit for the size of metadata is only about 2 kilobytes per object. So yeah, I mean, that's subject to confirmation, but that's what I've heard from the Pawsey team, is that 2 kilobytes. Now, I'm not sure if it's 2 kilobytes per key or 2 kilobytes per file, but I think it's 2 kilobytes per object. So there is a limited amount of metadata storage that you have. So it's not, it's not, it does have a finite limit, the amount of metadata that you can associate with an object. So metadata is only created when an object is created. And so if a file is already on the object store, so this is important. If a file is already there, then this command is not going to have any effect on changing the metadata. And that's because the file already lives on Acacia. It already has the timestamp and the size that is the same as the local file. And when you try to do this command again, it won't actually copy the new metadata in there because it's decided not to copy the file. So that's why, we've got a bit of complexity there. So metadata is only created when an object is created. You can add a flag called noCheckDest. So you could have added the flag noCheckDest to this command, and then that would have ignored the file size and the timestamp, and that would have forced it to copy again. So the MinIO client uses the stat command to download the metadata, and there's a JSON flag that you can include to make the output in JSON format. And so this is where we had a bit of problems with updating the metadata. So I've just included this extra line to remove any existing temp file if it was there. So this may have caused a problem, Josephine, I'm not sure, but it's possible that a temp file was already there, and then we tried to move to the temp file and it didn't do the move. So it didn't copy the metadata. So so we just remove that temp file first, and then we stat our file. We move our object on Acacia to a temp object or temporary object, and then on the move back, then we can set new attributes. So this is the way where we can update the metadata on an object. We move the object to a temporary object, and then we move it back. But when we move it back, we have the opportunity to change the attributes, because then that makes a new object. So only MC appears to have the ability to apply metadata during a move operation. And this comes back to how we don't have a perfect tool. And so you've got to leverage the advantages of either MC or Rclone. I thought constructing URLs was a pretty nifty feature that can help you share data with other people. And so with MC, it's just MC share download, for example. We're sharing a download link so people can just download whatever that we've given them access to on Acacia. So Rclone is pretty similar, but MC allows you to create an upload link so people can upload to an object on Acacia. Removing objects. Both MC and Rclone have the ability to remove individual objects. So with MC, it's just RM, but with Rclone, it's delete. So MC is a little blunt when it comes to selecting specific files for deletion. So you can delete everything that starts with data underscore, for example, by using the MCRM recursive and then force options. Rclone's a little bit more sophisticated in being able to filter things specifically for deletion. So you just use the include. So Rclone delete Acacia mine, which is the alias colon bucket name, and then include data star.dat. So that removes all the dat files from our test bucket. Now onto synchronization. So object storage is flat, but we can replicate a directory structure using those pseudo folders. So we've already covered that. But both MC and Rclone have the ability to recursively synchronize a directory to the object store. And each, while doing this mirror or synchronize, will only copy files that need to be copied. So again, we have the timestamp and file size determination whether or not we copy. So recent Pawsey experience suggests that Rclone is a more robust tool for this task, but there is a huge caveat. So when we scroll down to here, we see commands to mirror a directory structure. In this case, we mirrored the contents of the simulation directory to a pseudo folder called test within our bucket. We can also do the same with Rclone using this command, and then there's the progress flag to replicate the behavior of MC. So it shows you what's being copied. With Rclone, you can specify, you can actually do more than one transfer at the same time. So you can start one transfer for one file, but another transfer for another file. And you can have those transfers running at the same time. Each transfer is its own HTTPS connection to Acacia. So if you've got heaps and heaps of small little files, then it can slow down because every file is a unique connection, and connections take time to build and tear down. MC has the ability to exclude certain files from your mirror, as does Rclone, and they're both done with the exclude flag. You can do checksums while mirroring using the MD5 command, also the MD5 argument for MC, and the checksum argument for Rclone. And you can use Rclone to check your mirror, just to make sure that everything has been mirrored. Now comes the caveat. Synchronizing your folder back from Acacia works in much the same way, but there's important differences here between MC and Rclone. If you have any files existing locally in your file system, and you try and mirror the contents of a pseudo folder from Acacia to a local folder, with MC, the mirror will try and preserve local folders. If there are existing files and folders with the same name as what is on Acacia, then you need to specify the override flag. So MC is very ginger in the way that, or very gentle in the way that it mirrors things back from Acacia. Rclone doesn't have the same level of tact when it comes to synchronizing directories. It will destructively synchronize a local directory if you try and synchronize a pseudo folder or the contents of a pseudo folder back to the local directory. And we saw that in this exercise. So we created the simulation2 temp. When we tried to mirror from Acacia mine to simulation, that left the temp directory there. But when we tried to do that with Rclone, it removed the temp directory. So it's not advisable to use Rclone sync to move data from Acacia to a local file system, as it could destroy data on your local file system. So when you're staging from Acacia, it's advisable to use a copy instead of a sync. So there was an exercise here where we could use Rclone to mirror the simulation directory to your chosen bucket name. So that was just enacting these commands up here. Checking the size and number of objects in a storage location. So you can do that through the portal. So at portal.pawsey.org.au. So you can check, for example, go back to Acacia, I can check that I have 2 buckets in my personal storage, and I have 100 objects, for example, in each. So this is where you can check how many buckets you have and how many objects are in each bucket. So you can do that through the portal. But you can also do it on the command line using Rclone size. So that will give you the size and number of all objects in a remote. Rclone size, you can also do that on a bucket to get the size and number of objects in a bucket. But you can also get the size of a number of objects in a pseudo folder. In this case, we're getting the size and number of objects in a pseudo folder called temp. We finished this tutorial by a brief conversation about permissions on project storage. Now, this is a work that's in progress. So the Pawsey team is working on some best practices for restricting permissions on objects in your group storage. So just a preliminary advice then is that you can make a bucket with locking enabled. So let's say you've got your project storage and you want to stop everyone from being able to delete a particular thing in that project storage. So if you want to make something in project storage read-only, the initial advice from the Pawsey team is to use locking. So there is a command called MC legal hold, and what that will do is if you have made a bucket with locking enabled, then that will set a sort of like a read-only status on something in your Acacia storage. So you've got a project alias, which is, see, remember how we set up an alias for your user storage? You can also set up an alias for your project storage. So the project alias might be courses01, for example. So we access something in Acacia at the Acacia path, so that would be including the bucket name, and then the pseudo folder, and then the object. So you can set a legal hold, which is equivalent to a read-only flag in Acacia using that command. So MC legal hold info, that checks the status of a particular thing in Acacia. And you can clear that legal hold from something in Acacia using the MC legal hold clear. So if someone else tries to remove something that's got a legal hold on it, they wouldn't be able to. Unless it's you, of course. So And if you need to share data with someone else outside your project, then you can use URLs. And you can look at, and this is a really advanced topic, you can look at policies and applying those policies to buckets and objects to share them in a very specific way. But that's definitely an advanced topic. And we finished up this tutorial by purging our bucket, and that's ready for the next one. So do we have any questions? How did you find how did you find that?
I didn't have any question. I thought it was.
Oh, cool. So yeah, so it was all good? Yep.
Yep.
Great. How about you, like it?
Yeah, everything is good.
Excellent. Okay, so we're ready for the final tutorial now. So we'll just go across to T3, Acacia in HPC workflows. And have a look at the HPC with Acacia. Okay. So until now, we've been using Rclone and the MinIO client on the command line. And you can certainly do things with Acacia that way on Pawsey systems. But there are more powerful ways to integrate Acacia into your HPC workflows. The problem, and it's not really a problem, but a feature of Setonix is that there's a time limit for files of 30 days on Scratch. And so object storage on Acacia is one of the primary means of doing longer term data storage at Pawsey. And by longer term, I mean the lifetime of the project. So storage on Acacia is not forever. It's just for as long as your project exists. Okay, there is some interesting things with Rclone and the tape archive. So the Unix utility tar is the tape archive program, and it used to be preparing data for uploading to a tape. But these days, you can use the tar program to create archives. So it's like files that are made up of files. And that allows you to aggregate files. So if you've got a heap of really small files, you can aggregate all those files into one file and then just upload that one file to Acacia. So this tutorial is going to be about using tar effectively, using tar in combination with Rclone, and then using those commands as part of job scripts to bring data in from Acacia to do a supercomputing job, and then to move data back out to Acacia. You need to be able to depend on each of these steps though. So your supercomputer job needs to be able to depend on the job that's bringing data in from Acacia. The job that's bringing data back out to Acacia needs to depend on the supercomputing job. And so in this tutorial, we're going to look at ways to leverage those job dependencies. So we've already prepared the mock data, and where we'll get you started is the mini tutorial on tar. So has everyone got that loaded? Or that particular exercise loaded, or sorry, that the HPC with Acacia notebook loaded?
Yep.
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 Okay. Okay, so we'll get you started now with the mini tutorial on tar. Now, which one's that, Josephine?
The enable a trial workflow using job dependencies.
Oh, okay, great. Yep, so where it says integrating object storage. Oh yeah, enabling a trial workflow.
Yeah.
Oh, brilliant. Yeah, that's a good place to stop because we need to recap that section. Did you try the different compression methods?
Yeah.
Oh, cool. Which one did you find was faster?
It was, I have the times.
Yep.
The ZCF
Oh yeah, yep.
was like 0.008 of a
Right.
second.
Yes.
And then the JCF was the next fastest, and then the CF was the slowest.
Right. Yep. That's interesting. Yeah, normally the bzip is the slowest compression. But see, the start. Yeah, normally bzip is the slowest compression. That's because I think it uses more resources to
Oh, wait,
compress
no,
things.
yeah, I was looking at the wrong
Yeah.
bit, but
Yeah.
there was hardly anything in it.
Yeah, okay.
But I think it's 'cause it's
Yeah.
not that big.
Yeah, on Setonix, the bzip 2 compression has had, a factor of a few times slower than the gzip one, but it's resulted in a better compression ratio. Yeah, it's more, I guess it uses more resources. But it's interesting that you got the same sort of runtime. So I might actually try that myself. Yeah, so if we time our tar CF, so we'll go to our simulation directory. Yep. Yep. Okay. All right, let's do our time tar CF. Yeah, so we get 0.125 seconds. But what's actually in simulation? Ah, we've only got one file. So we must have deleted. I must have deleted something. Do you want to check your directory as well, Josephine, just to see? What sort of data you've got? Oh, okay. Yeah, my directory's been messed up for some reason. I'm not sure why. Just unzip. Unzip. So I'm just getting my data back.
I've got 10 files and then the test folder in results, and then the log file's empty. Folder's empty.
Oh yeah.
Simulation.
Okay. So you might want to unzip that data directory again. So just do what I did. So if we go up to one level again, just unzip the Acacia training.zip and yeah, unzip Acacia training.zip and then go yes to all. So go unzip Acacia training.zip and that says replace. So do you want to replace things? So we go A for all. There we go. And now if you go down to Acacia training and then data and then simulation, you should have all the files and results. So there we have all 100 files again. Okay, so let's try timing that now with tar CF. So we'll go time tar CF simulation.tar. So there we go. So we took 0.475 seconds. So now let's try the compression options. So we use tar ZCF, so that uses gzip. Okay, so we've got 0.595. Now we'll try tar JCF, which uses the bzip2 compression. And that got 4.648 seconds. Did you get something similar?
Just still running the last one.
Yep.
Yep, I got something similar.
Yeah, me too.
Excellent, excellent. So yeah, so the bzip2 compression is by far the slowest. But let's have a look at the size of the file. So we go disk usage human readable simulation.tar, and that's 106 meg for the raw tar file. Right, let's try the gzip. That's 160 kilobytes. Now let's try the bz2. That's 12 kilobytes. Now the reason why we're getting such extreme compression ratios is that this binary data is just full of zeros. So that's why we're getting huge compression ratios. By compression ratios, I mean the input divided by the output size. So yeah, binary data or data that has a lot of redundancy in it, so repeating things, they will compress better than things where there's no sort of patterns. So yeah, so binary data without many patterns in it. What I mean by patterns is in a bitwise sense. So random binary data won't compress very well. Okay. So before we get to the exercise, let's just do a recap of this particular module. And so we've prepared our mock data, and we just had to verify, because we must have deleted some before, but we just had to verify that the data was there. And then we just went through a mini tutorial on using tar. So tar files are useful when you may have so many files in your storage that trying to store them all in Acacia will exceed the nominal limit of 100,000 objects per bucket. Tar is useful when there might be a performance benefit in aggregating a large number of small files into a bigger file. You see, each upload to Acacia is a unique HTTPS connection, which takes time to set up and tear down. Tar is useful when you don't need individual access to files and when you need to preserve empty directories, because Acacia can't store empty directories very well. I just might pause. Can anyone see my video correctly? I think I've got problems with my video.
You seem fine.
Yeah, everything is fine.
Everything's fine? Okay, that's fine. I won't worry about it. It's just that on my end, my Zoom client, the video has paused. But if you guys can see my video okay, then I am not too concerned. Okay, sorry about that for the editing. So when do we use compression with tar? So tar files can be compressed as well. And there's sometimes a benefit for, compressing tar files. But for many types of binary data, the space that you'll save through compression is often marginal. So we've got our command for creating a tar archive. The C means create, and the F means there's going to be a file name. So we're sending our things to include to output name.tar. So for example, we'll use tar-cf simulation.tar, and we are tarring up the simulation directory. So that's this one here that lives within data. You can tar everything in the current directory, but I would put the output tar somewhere else other than the current directory. Otherwise, it gives me a warning about the tar file that I'm trying to create is trying to include itself in the archive. So if I go to simulation and then I go tar-cf without the ... simulation.tar, and then it will say simulation.tar files in the archive, not dumped. But if I move the output tar file to the level above, then I don't get that warning. So the V flag is verbosity. So let's go back to our data directory. So the V flag is verbosity. So if we do tar-cvf simulation.tar, then we just show everything that's being tarred. You can use the Z flag or the J flag while creating or extracting archives to compress or decompress a tar file. But the important things to note is that when you are compressing a tar archive, or you've created a compressed tar archive, you can't add things to that tar archive. So once it's compressed, you can't change things in a tar archive unless you decompress it. So these are ways to create a tar archive. And we saw that we saw that the time to create the tar archive with bzip2 is quite a lot slower than if we use gzip. But the bzip2 compression method produced the smallest file size. So if we go time tar cf simulation.tar simulation, we get this. But if we then used bzip, and then we did simulation.tar.gz, we get this time. And if we use bzip2, then we get this time. So that's taken quite a long time. I think that's a bit of an anomaly, but in this instance, trying to compress the tar archive with bzip2 has taken about 9 times longer than compressing than creating a tar archive without compression. So there is, when you are creating a tar archive, you can use parallel, so you can use multiple cores to do your compressing or decompressing. So there's a program out there called PigZ, which is the parallel implementation of gzip, so PigZ. And whenever you're creating an archive, you can use the compress program PigZ, and then that will compress in parallel your tar archive. So that's actually taken less time to use PigZ than it actually takes to create the archive without compression. And that's probably because you're compressing in parallel, but the time required to write that compressed is a lot less than when you are trying to just write out the tar archive. So that's why using PigZ has actually resulted in a faster time of compression than without compressing. So of course you can use PigZ on the decompression step as well. And so PigZ will use all available cores that are on your machine or on your node in your job, for example. So we just did some more exercise about excluding files from an archive, listing an archive contents using the T flag, extracting archives using the X flag, and you can extract files from a compressed archive using the tar xj command for a bzip2 compressed archive, or tar xzvf for a gzip compressed tar archive. So that's extraction. We use tar xvf, but if the tar archive is compressed, we use either the Z or J flag. Adding files to an archive is accomplished using the R flag, and we just made a new directory called simulation2 and added it to the tar archive. We can also delete things from a tar archive, and we can use the compare option to see if there's any differences between what is in an archive and what is on disk. But comparison is not a recursive operation, so we just need so comparison is not a recursive operation. So there's a little exercise here where we deleted a file from the tar archive, and then we made a new file, and then when we used tar compare, it showed us what the differences were between the simulation.tar simulations.tar and the directory simulation results. So yeah, that's what I meant when I said when you try comparing a tar archive to a certain location, it's not recursive. So you have to be specific what you want compared within a tar archive. Okay, so this is potentially interesting as well as streaming a tar archive to and from Acacia. So with tar, you're creating this intermediary tar file. But if you use the hyphen, you can actually send the output of tar to standard out. Or you can receive from standard in a stream and send that to tar for extraction. So what's happening here is that I am using tar to create a tar archive, but instead of a file name after the F flag, I'm using this dash or hyphen. And that tells tar to use standard output as the output for the tar archive. Then I'm piping to Rclone, and the rcat command takes standard input, and that sends that input to a file object on Acacia. So that is a way to do a tar archive on the fly to a file object in Acacia. So you can bypass the middle step. You can even use PIGZ, and yeah, you can even use PIGZ for multi-core compression. So using the number of available cores in your job, you can send the output from tar to the input of Rclone, but you can use the compression program PIGZ, and then that sends the resulting compressed tar archive straight to Acacia as a file object. So tar, PIGZ, and Rclone can work together to stream tar archives directly to Acacia. I wouldn't recommend streaming, though, for mission-critical applications or applications where your computer sending data to Acacia is not on the Pawsey network. So the Pawsey network is, quite reliable. So if you're on a Pawsey machine such as Setonix, you might be able to get away with streaming tar files directly to Acacia. The Rclone cat command, as opposed to rcat, the Rclone cat command turns Rclone into a source. So that means that the output from Rclone cat can be used as the input for something else, like tar. So Rclone cat, we're streaming our simulation.tar file from Acacia into the standard input of tar. And because we're using a hyphen there instead of a file name, that means we are using standard input or standard output, depending on this C or X flag. So if we're using an X flag, tar would expect standard input. Okay, so this one here is streaming from Acacia a compressed tar archive, and we're sending it to tar and the results, or the results of the contents of that compressed tar archive will go into simulation 2, and we're using the decompression program PIGZ. So that's combining those commands together again with rclone cat. When you're streaming to an S3 backend such as Acacia, the uploads are chunked. So if you're using rclone copy, for example, so I don't just mean tar streaming in this context, but when you're sending a file to Acacia using an S3 backend, the uploads are chunked. So the upload is chunked into a hard limit of 10,000 chunks. And that is an artifact of the S3 protocol. So the Amazon S3 protocol divides up files into 10,000 chunks. And by default, the Rclone and MC clients have a chunk size of 5 megabytes. So that gives a maximum file size that you can send to Acacia if you don't do any changes to the configuration of just under 50 gigabytes. Okay. So you can increase the chunk size. Yeah, you can increase the chunk size for Rclone by adding the line chunk size equals 1G to every remote in my config rclone.conf. So if I go to config, change directory to Rclone, and there's my config file for Rclone. See how I've got this chunk size of 1 gig here? I need to add that chunk size of 1 gig to my entry for Acacia Mine. And that will increase the file size that I can upload from around 50 gigabytes to 10 terabytes or tebibytes. Yeah. So that's important to know. You need to be able to vary the chunk size in order to increase the maximum allowed file size to just under 10 tebibytes. So a little bit of streaming performance testing. So from HPC Data, which is another computer on Pawsey, I was able to upload around 50 gigs of files to Acacia using task streaming at a rate of around 130 megabytes a second. But there are no integrity checks with task streaming. So if you want integrity checks, what I recommend to do is that you create an intermediary tar file, and then you use MD5 checksumming in order to send those files across to Acacia. With Rclone Sync, I was able to increase the transfer rate of a directory structure to around 671 megabytes a second. But using Rclone Sync, of course, you need multiple files to be able to do parallel transfers. So these are the kind of streaming rates that you can expect within Pawsey until they upgrade the clients. So I am aware that there is a new client being developed for working with Acacia, and that should increase the streaming rate that data can be sent to Acacia. All right, so moving on to the final exercise. So Scratch is not for long-term access. So it's advantageous to incorporate Acacia into your Pawsey supercomputer workflows. So Acacia can be both the origin and destination for data that is processed on a Pawsey supercomputer. So data is staged from Acacia to Scratch. Your job is run, and then process data is then stored back to Acacia, where it can be accessed from anywhere. There are two things that you can use to make this work. You can use job dependencies and the copy queues. So a typical supercomputer job might look like this. So you've got your script, you're using a particular account, you're using a work queue for your supercomputer job, and you're choosing two nodes. N task per node is the number of MPI tasks that you have per node, and CPU task is the number of OpenMP threads per MPI task. So we would load some tool and then srun the application that we're using for our supercomputer job. So when we run this job, it's normally sbatch superscript. So my supercomputer job script, and that produces a job ID. So whenever you sbatch a job, you're getting a job ID as the output. If you use sbatch with the parsable flag, then you just get the job ID. And you can capture that job ID and use it as a dependency for the next script. So let's capture the job ID from the submission of a script. So let's say that we have a script that stages data using any of the commands we previously talked about. Let's just say that stage script stages data from Acacia into Scratch. So we submit that script using sbatch parsable, and then we pipe the output to cut and get the first field. So we don't really need to use the cut command in this instance, but sometimes there is more than one output from sbatch parsable. So that will give us the stage job ID. You can use that ID when you are submitting the next script. So we go sbatch, so scrolling down, we go sbatch, and then we have this flag dependency equals after OK, followed by a colon, then the job ID of our staging script. So this is how we create the dependency chain. But you must specify the dependency flags before you specify the name of your script. So here we are grabbing our super job ID by submitting the superscript, but we must depend on the ID of the staging job. And then we're piping that output to cut, and then that gives our super job ID. When you want to store the data back from your supercomputing job, you can repeat this, but instead you are depending on the super job. So we've got our we've got our storing script. So that stores back out to Acacia. And that might use, for example, Rclone, cat, and tar together. This is our storing script. And what we do is when we submit our store job, we depend on the super job. So the stage job is initially run. Our supercomputing job depends on the stage job, and then our store job depends on the super job. So we've got our dependency chain there. So this script here depends on this script, and this script depends on this script. So what we're doing with the exercise is that we have in the scripts directory, we have 4 scripts. So we have our stage script. So this is our stage script. We have our superscript, and then we have our store script. And to bring them all together, we have our master workflow, which does the running of each script and tracks those dependencies. So what your job is that we're going to create on Acacia. So we're going to change directory to our data directory. So there's our data directory. And we're going to change directory to data. And what we're going to do is we're going to stream the simulation directory and compress it. And we're going to send that to Acacia into our bucket name. So hopefully we still have the bucket name environment variable defined. There we go. So we have streamed the simulation directory to Acacia. So if we go Rclone ls Acacia mine, and then bucket name, we have the simulation.tar.gz file on Acacia. So that is located at the path Acacia mine, bucket name, and then / simulation.tar.gz. So what we have to do is we have to edit the stage script, the superscript, and the store script. And every time we see curly brackets, we have to make the right substitution. So if we go to account, we could substitute in courses 01, for example. So that's the account. That's the account name. And as Alexis was saying, this inside these scripts is where you put module load commands. So in this case, we're going to load Rclone 1.58.1. And we make a scratch directory. So in this case, it's going to be scratch courses 01 COU 001. That's for me, but your course will be different. And then we replace our alias, which would be Acacia mine. And then what is our Acacia input path? Well, in my case, it's going to be courses 01 Acacia TMP, and then simulation.tar.gz. Yeah, so what you need to do is go through those 3 scripts and replace anything in curly brackets with information that you need in order to make these scripts run. So this is the information that you need to provide. So with account, you replace courses 001. Acacia alias is your alias, and that's Acacia mine. Acacia in path, Acacia out path, the name of the copy queue. So if we go to the stage script, see how we're using copy queue? So on Zeus, the copy queue is actually just written as copy queue. But on Setonix, the name of the copy queue is just called copy. Yeah, so we just have to replace this relevant information in those scripts. And then when all that is done, you should just be able to run this master script and have the supercomputing job depend on the stage job, and then the store job depend on the supercomputing job. And then when it comes time to running these scripts, you should be able to, when you run them, you should be able to see that when you run the script, there is a dependency on the staging script, and then the storing script has a dependency on the supercomputer job. So does that sound doable? Any thoughts on this one?
Looks okay, not bad.
Yeah, it's not
Yeah.
too bad at all. You just have to supply the missing information really in each of these scripts. Yeah, so it's just a matter of editing those 3 scripts and then running the master workflow. And success will look something like that. All right, so I'm going to do the exercise along with you. So I'm going to change our account, which is courses 01. On Zeus, the copy partition is called copy queue. And my Scratch directory can be anything that you have access to, but I'm going to call it Scratch courses 01, COU 001, and then working. So I'm just calling my directory working inside my Scratch space. So the stage script creates the working directory and then copies the simulation.tar.gz across from Acacia. It streams it to tar, but it uses the parallel compression program PigZ to do the decompressing. So that seems to look okay for my staging script. Let's have a look at the superscript. On Zeus, the debug queue is called debug queue, and that looks fine. Now I'm changing the store script. Okay, now the good thing to use with dependencies and these staging and storing scripts is that when you use the copy queue, see how I'm using copy queue here? When I'm using a copy queue, it doesn't actually count towards my allocation. So I could have, of course, put these staging and storing work, such as this one here. I could have put the staging and storing work into the supercomputing script, but I would be using some of my allocation on I/O. So that's not very good. But if I use the copy script, or if I use the copy partition on both Setonix and other machines, if I use the copy partition, then the time spent doing I/O doesn't count towards my allocation. So it's a good way to save on my allocation that way. Now, of course, I've edited these files locally, but you'll have to edit your files on Zeus itself. So you just need to go to the scripts directory. Oh, that's interesting.
Yeah, I only have one script I can edit.
Yeah, me too. I'll see if we can fix that. Yeah, I'm not sure why that has happened. On your local copy on your machine, you see the scripts.
Yeah, I can edit them off of Zeus.
Yeah. Let's have a look. It might be working against the 30-day scratch retention policy. Yes, that's what's happened, Josephine. So see, I'm just having a look at the modification date on superscript.shell, and it was set for the 29th of July. So that's the last time that this has been edited or modified. So yeah, so we're actually being affected by the retention policy on Scratch. So I've brought a file out of Acacia, but when I unzipped it, it must have retained the retention policy. So it must have retained the modification time on the scripts. So if we just touch those scripts now, and that's updated the modification time to now. It should be okay.
So I just unzip everything.
Yeah, re-unzip everything, and then what you do is you use the touch command to touch those files, and then that updates the modification time.
So I just do touch.
Yep.
Okay.
Yeah, so you can actually do that with everything inside this directory. So go touch star, and then that should update the modification time of the files, so they won't start disappearing on us. But that's something you have to be mindful of when you're bringing things out of Acacia, is just to make sure that, yeah, that the modification time, if it's old, then it will get deleted in Scratch. Yep, so I'm just going to copy. Just going to copy what I have. I'll make a oh, it's not good. There we go. So there's my stage script.
Hello.
Hey, how you doing, Wicked?
Yeah, I'm sorry, I'm Alexis. I'm sorry, Toby.
Oh, sorry, Alexis. Yep.
I have been trying to speak, but the microphone was not working. So
Oh,
what happened was that your files were originally in Acacia or were in a zip, in a tar file?
they're in a zip file. So
they are coming
yeah,
from, yeah,
they were on.
okay.
It's really it's really interesting. They were zipped up last night. They were zipped up last night, put into a zip file, and then that zip file was uploaded to Acacia. And during the unzip process, it appears to have preserved the modification time.
Mm-hmm.
So old files were being progressively deleted.
Yeah.
Yeah, so we were working against the retention policy.
Yeah, so we need to find, I'm not an expert in tar, but we need to find a way of extracting without preserving the dates, because that's going to be an issue.
Yeah, absolutely. There must be a flag to the unzip.
Yeah, because MC has a way of preserving information when copying data into Acacia, but I found the same issue. If you preserve the preservation is preserve everything or nothing. So what we wanted to try was to preserve the privileges on the file, like the write execute privileges.
Oh yes. Yeah.
So so you can preserve those, but then you also preserve the date, and then when extracting them back into Scratch, then you will face that issue. So I guess the same thing should be done for tarring and on-tarring, like not specifying a non-preserving of the timestamp.
Yep. Yeah, that's true. Yeah. Yep. So even the course material got affected by by retention policy. Yeah, that was certainly interesting but unexpected.
I will try to find the tar option now, just to for complete.
Oops. Yep. So there's an error in my script. So I didn't use debug queue instead of debug queue. All right, so we go. Oops, sorry, that's these. There we are, fixing the error. There we go. So there is the dependency flow. So we've made the necessary changes to each of the scripts. And for our supercomputing job, we are depending on the stage script, and the storing script is depending on the supercomputing job. So yeah, how are you going with that, Josephine?
I think I'm getting
there. Yeah. Oh, that's great.
the output file.
Oh, excellent. Yep. So were you able to get the output similar to what was similar to what we saw?
Yes, I got the
dependency chain.
Out.
Hey, that's awesome, Josephine. How about you, Wykit?
Yeah, I got a similar one as the one shown on the screen.
Hey, nice work. No, that's really cool. So what you guys are doing now is you're successfully set up the dependency chain between staging, the supercomputer script, and the store script. So no, that's really cool. There is one more. There is one more script to try if you want to do the final exercise. It's even easier actually than the one you just did. If you look at advanced workflow.shell, so if you look at the advanced workflow, this is actually combining those 3 scripts into one, because I find it's easier and less prone to errors actually if I just specify the information once. So all you have to do with the advanced script is just supply the account, which is courses 01, so that's already there. The alias, which is Acacia mine, but you just have to supply the bucket name. And so that's just your bucket name. And that's all that you need to change actually. All the rest in here just does the same job as that master workflow, but it replaces all that information in there. But you can use this advanced workflow for your own purposes. So if I hadn't specified the Acacia in path, for example, so if I'd left this bit blank, it wouldn't actually run the staging script, but it would run the supercomputing script and the storing script. Alternatively, if you don't specify the out path, then it won't run the store script. And if you don't want to run the supercomputing script, you just type run super is equal to nothing. And then that won't run the supercomputing job. So you can edit this script as much as you need to. And it uses the bash heredoc syntax to create the staging script, the supercomputing script and the store script. So it creates those and just puts them into a variable. And then it runs those scripts down here. Just from some bash syntax. So it's running those scripts as strings. Yeah, so these advanced scripts are kind of like take-home scripts if you'd like to use them for your own workflows. But for the exercise, I think all you have to do is specify the bucket name.
Yeah, I got it to run.
Ah, excellent. Oops. Yeah. It's really good. Yeah, so we figured out the problem with the disappearing course material. When you do the unzip, so I'll just go to where it says L5 mock data. Whenever you unzip the Acacia training material on Scratch, you have to use the -dd flag, and that will unzip the material, but set the modification date to now, so that we don't have any problems with with grabbing things from the zip file. Okay, so I'm just going to do a little bit more housekeeping, but what I'll do, Josephine and Wykid, is probably by close of business today, I'll upload a new copy of the course material, and you can have the latest version with some of these corrections from today in there.
Okay.
Okay, sure.
Yep. Yeah. So were both of you able to run the advanced exercise?
Yep.
Yeah.
Yep, I know. Ah, excellent. All right. Well, that concludes today's training. Oh, well, so I might bring the recording to a close.